Hi there, this is Sayan from IIT Kanpur. Welcome to a new and attractive video series called Cell in Focus by Bioorganic Hub. I am here today with you to tell the story of a special type of electron microscope called a scanning electron microscope. So, scanning electron microscope is a very important technique to get a subatomic details of the surface of a nanomaterials as well as some biomaterials. So this is very important technique for the nanotechnology as well as biomaterial research. So just let's start. As you can understand from the name electron microscopy, so the name suggests electron will interact with the matters, with the materials of your specimen. So when electrons are interacting, there will be no colored image, only black and white image you will get. Okay, so one thing to mention that for scanning electron microscopy, unlike transmission electron microscopy, only surface information you will get, upper surface informations. So electron, in a very lucid manner to say, for scanning electron microscopy, electron comes, fall on the surface of the specimen, make some interactions of the atoms of a material of your specimen which presents at the surface or near surface, make some interactions and again come back with some new form. Okay, so this coming back electron are going to be captured by some detector which actually contributes to the image formation. So this coming back electrons depends upon how much interactions are happening. Okay, and this depends upon too many factors. So scattering range of electrons inside the specimen is different. That actually making different contrast, different amount of dark and bright spot in your image. That's how image is forming in a single sentence. So this scattering range of electron inside the specimen, not very inside, just the near surface or the surface of the specimen is different. That depends upon many factors. One is the electron energy. How much electron energy that particular point of that specimen are getting. That depends, that decides how much electrons are coming back. What is the type of that electron? What is the character? Now next is the atomic number of that elements making up the specimen. Atoms which are helping to build up the specimen, that decides what will be the character of the coming back electron, returning electron, and that actually differs. And that's why in the image different spots are forming. One is more darker, one is less darker, one is more bright, one is less bright. Another is the density of the constituted element. Let's say in one place you have many atoms, in another place you have less number of atoms. Let's say same atoms. So where you have many atoms, the scattering will be less or more as compared to the other. So the dark or bright spot in your image for that concerned points, concerned 2 points will be completely different. That's why the images are formed. Okay. Now, as the name suggests, electron microscopy. So electron microscopy means electrons are going to interact with your material. So electron when interacts with the material, it will create, unlike a light microscopy, black and white image, and that has been created normally by contrast formation. Okay, so whenever you are getting black and white image, this is bad, as like you are not getting colored image. But you know, older gold. That's why for black and white, like old picture, you will get a subatomic resolutions of your particles. You will get more intricate details in an atomic level. That's why SEM is more important technique as compared to light microscopy to investigate cellular details, investigate nanometer resolution details. Same, just to give you the information, same can magnify one particles to 300,000 times. Okay. And light microscopy can only magnify one particles to 2000 times, and transmission electron microscopy can do a huge amount, 3 million times magnifications of a single point can be done by transmission electron microscopy. So TEM and SEM both are very well to get the intricate details of the species. Now this slide shows a black and white image of the SEM. So this is a particular SEM image of something, of some virus. So here you can see these 5 similar things, the sphere things are actually denoting the virus. This image has been taken from researchgate.net. So the dark spherical periphery actually denoting some less or more scattered. That's the difference in scattering of the inner bright spot and the outer dark periphery. Okay, so this dark periphery scattering pattern is different from the inner bright periphery. That's why the images are formed. And here the sphere are denoting the virus present on the surface. And you will be amazed that this is nothing but the same image of the surface of very well known killer of 2019, SARS-CoV-19. This is the same image of coronavirus SARS-CoV-19. Now you will be curious how the image is formed in the scanning electron microscopy. That we will see in the next slide. You will be very much curious to know how the image is formed in a SEM instrumentations. So this slide shows the particular SEM microscope, the instrumentations of the scanning electron microscope. Here you can see as electron is involved, you need an electron source. So at the top of the microscope there is an electron gun. So electron gun actually helps to generate the electrons, and these electrons are going to be attracted by a anode which placed very nearby. Anode is the positively charged and electron are negatively charged. That's why anode attracts all the electrons. Now after that electrons are going or pass through the vacuum present inside the microscope. Now as the vacuum are inside the microscope, you can't use light, you can't use glass lens as like light to make a well-mannered beam. Okay, that's why people use as like the transmission electron microscopy. Here also people use a magnetic lens or electromagnet to focus all the beams. So that converts the electrons to a well-mannered focused beam, and again that is more converged by using a scanning coils. Then what happens? The focused beam of electrons fall on the surface of the specimen and they are making some interactions we will discuss in a minute. After making some interactions, there will be coming back electron, some type of coming back electron that has been denoted by SE and BSE, which is called scattered electron and the back scattered electron. What is that? We will see in a minute. So this scattered electron and backscattered electron comes back from the specimen and going to be captured by some detector which helps to form the image. Now one question obviously is going on your mind. What is the scattered electron? What is the backscattered electron? Exactly, we are coming in that questions. So this slide shows when the electrons are knocked off near the surface or reflected from the surface of the sample, that knocked off electron is actually used for the image formation. So as the picture here shows, this is an incoming electron beam which has been denoted by a yellow beam. Now whenever an electron beam comes and making an interactions with the materials, 3 types of interactions can happen. Again, taking reference from my another video, transmission electron microscopy, 3 types of interactions can happen. One is with no disturbance, electron beam will just go and pass throughout the sample, and that will not happen for the case of scanning electron microscopy. Another 2 types of collisions, that is inelastic collision and the elastic collision, will happen here. So first scattered electron is called a backscattered electron, and that actually happens by the elastic scattering. So what happens in elastic scattering? By definitions, when two bodies make an elastic collision, there will be no change of energy, no change of speed, but only thing will change the propagation path of the beam. So here also the beam will bend, but in case of same, the beam will bend so much that it returns back towards the observer. So that's why it's called backscattered electron. And this comes from the deeper region of the sample. Mind it, deeper region means not inner side of the surface, that actually near surface or the upper surface. So that goes some extent deep below the surface. And that's why backscattered electron are actually gives us the informations about some extent deeper of the surface. And this actually depends upon the atomic number. Let's say you have a carbon and you have a chlorine. So carbon has less number of electrons and chlorine have more number of electrons. This will change the scattered pattern of the electrons. The backscattered electron from a chlorine, from a carbon will be different exactly. And that will make a difference in your image. Maybe one will be more darker or more brighter, another will be less darker or less brighter. That will be reflected in your image. So backscattered electron contributes directly to the image formations, and this gives some informations about quite deeper from the surface. And another electron is the secondary electron, which is actually happens for the inelastic scattering. Two types of scattering, elastic and inelastic. Inelastic scattering happens, which creates the secondary electrons, which exactly comes from the surface. So here the secondary electron gives only surface information, and this comes from the surface. So here you can understand secondary electron and the backscattered electron are actually conveying two different type of information of your specimen, and those two informations are going to be collected by some special type of detector. We will not go in inner details, inner mechanism of this detector, but here suffice to say that this detector use something which collects these two types of electron and accelerate it before reaching the photomultiplier tube for amplification, and thus image formations happens. But you will be curious how the image formation happens exactly. Now this is the inner mechanism, but how exactly image formation happens, and that we will discuss in the next slide. So scattered electron and the backscattered electron both contributes for the image formation. Now how the image formation happens? Okay, that the mechanism of image formation actually happens by the raster pattern of signal acquisition that has been shown in the next slide. So what is the raster pattern of signal acquisition? If you want to know that one, please listen carefully the story I will say now. Okay, so the story is, let's say you are a person are standing in a room, in a dark room, and you want to search some photo frame which are hanged on the wall of the room. You don't know in which wall the photo frame are hanged. Now you have a torch, obviously you have a battery on this torch, otherwise you can't do anything. So you will do what? You will light up the torch and you want to search the whole room for that photo frame. When you know the photo frame is hang on the wall, then you will search only the walls. So how you will start? You will start from the upper corner of the wall, and you will go throughout the row, means throughout the wall. One row will be completed, then next row we will cover up, then next row, and thus you will cover all the height of the wall. One wall will be covered, then next wall, next wall, next wall. So 4 walls will be covered. Obviously photo frame is not hanged from the roof, so you will not take any light on the roof. So this pattern exactly follows in the raster pattern of image acquisitions. Let's say you have a n cross m matrix. M and n doesn't need to be equal, and you are making acquisition of signal and giving the image to fill up each elements of the matrix. Here in the left hand side picture you can see the elements are going to be filled up by the signal acquisitions. The last row are going to be filled up. Now it's filling up, had finished. All the row has been finished. There are particular image for a particular species. I also don't know what is that. So the row are forming. This row are making image, a row are making signal acquisition. Now here in the left hand side, here in the right hand side picture, here you can see all the row, all the elements has been figured out. Now only the last row has been left and the penultimate row, some elements. By this it will figure out all the row, all the columns, and then again start from the starting, the point number, element number 1 1, and then 1 2 1 3 dot 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 1 n, again 2 1 2 2 dot 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 2 n. So this is called raster pattern of signal acquisition. So obviously one question I know is going on your mind, when the image will be acquired in this manner, 1 1 1 2, obviously it will many time. Okay, actually not. Same is actually a magic. It happens in a nanometer scale. It happens in the nanometer scale because all the things, signal acquisition, electron beam propagations, and the correcting of the electron beam pathway, that all the things happens in a simultaneous manner. In that perspective, same is a magic. But it meticulous also. Why? Because you need to be focused the electron beam very properly, which decides your resolutions of your sample. Also you have to choose your sample covering on the dish on which you are covering your sample very carefully. Okay, so they are meticulous also. So one thing to mention, that you are getting a subatomic resolutions, you are getting very finer details in atomic resolutions of your surface. So everything you are good, you are getting, but all the things you good cannot get. So there will be obviously some disadvantage when you are using electron. Okay, that disadvantage we will see in the next slide. That's called consequence of using electrons. When you are using electrons, electrons are actually charged particle. So same can only be applicable for the conductive samples. If you have non-conductive nanomaterial, you can't do that. That's why in the filling of form for same, they ask in the form whether your sample is conductive or not. Okay, so only applicable for a conductive sample. And whenever you have the vacuum inside the microscope, you can't use any samples, because vacuum, it will evaporate, isn't? So liquids and limited organics, no liquid can be used in that space, and limited organics can be used in vacuum. So that's the drawback of the same. So hopefully you have understood all the concept for the scanning electron microscope. That's all for scanning electron microscope. Hope you understood all the concept and enjoyed throughout the video. If you have any questions, if you have any doubt, please feel free to mail me. I have mail in my descriptions of the video. And if you have any questions, you can also comment. I want at least 5 to 10 comments from this video. Okay, yeah, if you have any questions, you can mail me. Thank you for watching. If you feel it helpful, please share and subscribe. Okay, bye bye.